We're doing chapter 6.3, nuclear fusion today, following the Walding textbook, which is the Queensland physics syllabus, unit 1, talking about radiation obviously, in particular nuclear fusion. You might like to pause as we go to look at the XKCD cartoons on the screen there. You can find them just at xkcd.com and they're usually quite good. Okay, let's have a think about what we're doing today. If the sun uses fusion reaction to produce energy, why is it that the sun doesn't get lighter in mass then? And the question is actually a good one because it does get lighter in mass. However, it's just that big that we don't notice it. It's losing something like 4 million tons of mass a second to fusion, to solar wind, solar flares and things like that. But it's going to keep shining for, we think, about another 5 billion years. But in that time, it's going to lose 0.034% of its mass. So it's still losing a lot of mass every second, but it's so big we just don't notice it. The second question there, in what way is nuclear fusion similar and different to cell fusion in biology? Cell fusion you can think of in biology like fertilization. For example, a sperm and an egg come together and fertilize to create an embryo. The two cells combine to create one. Fusion's a little bit like that, but it's a bit different. It's two atoms combining together to create a new, bigger atom, but there's a heap of energy released at the same time. And last time I had a go at biologists saying that it was just a bunch of cells gossiping about other cells. Perhaps you could think about how physicists, maybe just a bunch of quarks, looking at describing other quarks. Righto, so what we're going to look at today is nuclear fusion and the reaction of fusion, how it occurs, and you'll be able to describe it. Okay? So fusion, as we've seen before briefly, is when two smaller nuclei fuse together to create a large one. So here's like an alpha particle, helium there, nitrogen there, fusing together to make this larger oxygen atom. And once again, if we look at the atomic numbers and mass numbers, it should balance. 2 protons plus 7 is 9. 8 of them are there with the oxygen, and 1 with this hydrogen that's released. And same with the mass numbers at the top there. 4 plus 14 is 18. 17 of them are there, 1 of them are there. We've got the same sort of arrangement over this side here, where the neutron is fusing with the nitrogen atom. It's a slightly different thing. When we think of fusion, we more think of, on the left-hand side there, 2 nuclei fusing together, but it is possible to have something like the one on the right there. Now, hydrogen fusion is actually kind of complicated. We often just think of it as a hydrogen plus a hydrogen becoming a helium. But there's actually a lot more steps to it. And it's worthwhile pausing the slide here and just have a look at these different steps that I've got here. Because I'm talking about deuterium and tritium here on the screen, producing helium and neutron and a bit of gamma radiation. And we've quantified there the amount of energy released in joules and mega electron volts. But it's not necessarily like that. You can see this one here, we're using 2 deuterium atoms, and so on. The diagram on the right is probably another way to look at it, a little bit more pictorial. We've got 2 hydrogens at the top here, 2 hydrogen protons combining, making a deuterium, all right, and a neutrino, and so on. Energy is released up there. It's worth pausing and just working your way through those, okay? Because we do have things like our positron in there. And remember, the positron is just like a positive electron. We saw that with radioactive decay a chapter or so ago. But the positron doesn't last long. It'll usually run into an electron before too long and annihilate itself. And when I say before too long, on our time scales, almost straight away. Let's look at an example, and this is going to follow some of the stuff we did in 6.2. Consider the fusion reaction, this one here, where we have a deuterium and a tritium. A deuterium, which is that guy, and a helium there, fusing together, and we get a helium and a hydrogen and some gamma radiation released. A, show that the energy released is 18.35 mega electron volts. B expresses in joules per atom and joules per kilogram. So think about the steps to do this, and it's worth pausing and just looking over your notes to get it in your brain. The more you do that and think ahead of where I'm talking, then the easier it is for you to understand each step. It follows exactly the way we solved the problems in the last section. So, part A. We can use the atomic masses of the nuclides, so the mass of the reactants and the mass of the products, and we find the mass defect. Okay, we've done that plenty of times before, so that should be revision for you. You can look at those numbers and see how they add up here. And when we subtract 5.03 from 5.01, as we're doing in there, these two numbers here came from these ones here. Here's our mass defect there. Notice it's a negative number because the energy is released, which we should expect because we have this gamma radiation released. We've got atomic mass units, 931.5 is our conversion factor to mega electron volts. There, that's revision from previous chapters. If you don't recall it, that's okay. Revise it again and you'll make sure it's in your brain. B, express this as joules per atom. So we want joules, so it's got to be an energy, E equals mc squared, our mass energy equivalence. Plug the numbers in. Here's our mass defect, multiply it by 1.66 by 10 to the negative 27 conversion factor, and the speed of light. When you plug that into your calculator, it all comes out in the wash, 2.94 by 10 to the negative 12 joules. And energy per kilogram is part C down the bottom here. So we've got the mass of an atom of our hydrogen, which is that guy there, comes from a data table. Multiply it by the conversion factor to put it into kilograms. Do 1 over that number. See that number there is this number here. It gives you that many atoms. So this is all revision from 6.2. Once you've got the number of atoms, multiply it by the energy, 2.94. That is that number there. He ended up in there. Plug it into your calculator and it comes out in the wash. 8.8 by 10 to the 14 joules. So when we think about fission, which is where they combine together, fission where the atom splits apart versus fusion where they combine together, we often think of this, there's energy released and we can use this. The main use for fission is nuclear reactors to generate electricity, generally pretty good. Fusion, probably one thing that comes to mind as most common is atomic bombs. Generally not so good if you're standing where it lands. So if we consider our reaction of main sequence stars that we saw before, let's think about this question here. How would you compare the energy released between reactions? So between fission and fusion, there is energy released per reactant, per atom that goes into it. That's your fuel you're starting with. Kind of like, which gives you your most bang for your buck out of this process? So just have a think about that for a moment. Last time we looked at how we calculate the energy released for these reactions. We've looked at it again in the previous few slides. I had this slide in the last section. This was in the 6.2, the previous one in the playlist for this. You can work out the mass defect of the reactions and work out which one gives you more energy given off. I encourage you to go and have a look at page 197 of your textbook, of the Walding textbook, and it'll actually step through all the calculations for this. It is worth, if you're looking at getting a really good ATAR, to try it yourself and see how you go and compare your answer with page 197 of the book. Connecting info and going back over stuff is really useful for your understanding of these topics. Here's the short summary, kind of like the Reader's Digest version, if I must. Reader's Digest used to make condensed books where they would shorten big long novels into shorter versions to make it easier for you to read. That's what I mean by the Reader's Digest version. Here's your little shortened version. So we're looking at joules per event and joules per kilogram of the reactant that you're using. So we have fission in the first column there, fusion in the second column. So if we look at the comparison column, this last one down here, if we look at the joules per actual fission, like actual event, fission gives off 7 times more energy than fusion per actual event. So actual, think of a uranium atom decaying and splitting apart. That's our fission. Will give you 7 times what fusion gives you, like say 2 hydrogens coming together. But if we look at the joules per kilogram, fusion gives you 8 times more energy than fission. All right? And the reason for that is the hydrogen atoms that you're fusing together are so much smaller, so hence you can fit more of them in your kilogram to then overall get more energy out of the whole reaction. And that's why fusion tends to give off more energy, because you can squeeze more hydrogen atoms into the space available, whereas uranium is quite a big atom and takes up a lot of space. Okay, so just a little bit of check your understanding. What's the difference between fission and fusion? What's the actual energy released, and which gives more energy per kilo? We did just talk about that. I hope you went and looked at the textbook, page 197, like I told you to. So, fission only produces more energy than it consumes in large nuclei. So you can really only split apart the nuclei. Remember that graph we've shown before where we have basically binding energy and it kind of goes in an angle like that, and you had lead right here in the middle. Everything over this side breaks apart, does the fission. Everything on this side fuses together. So fusion only produces more energy than it consumes in small nuclei. In large nuclei, it just doesn't give you energy released. Fission releases the energy of the electromagnetic force when positively charged particles of the nucleus fly away from each other. Okay? Fusion releases the energy of the strong force, which is very, very strong at short distances, and we looked at the strong nuclear force in previous chapters. So it comes back to releasing the energy of this strong force and physically in the actual atom. And don't forget our little data table that kind of summarizes it for us. So from here, have a look at the Check Your Learning 6.3, have a look at the chapter review, and you can wrap up the chapter. Thanks for coming.